Hi, good afternoon. Thank you for joining again. Welcome to the workshop about explainable AI in power generation and distribution. There was a keynote on the topic in the morning already, but now in the workshop I will go deeper and focus on showcasing the real-world use cases in the form of live demos. That will be the focus here. So let's take a quick look at the agenda. I will start by giving a quick introduction. What is explainable AI? What is the role of humans in explainable AI projects? For those of you who attended the keynote already, there will be a bit of an overlap here. Sorry for that, but it's only a short part. The main content is afterwards. This is about the real world use cases. We have one from Verbund, one from ENBW, and the third one. And they illustrate applications from our experience that benefit from having humans in the loop. Finally, there will be a conclusion followed by a Q&A session. Please feel free to post questions in the chat at any time. Yeah? So during the talk, afterwards, whenever, just in the chat. But first, who am I? I'm Thomas Mühlbacher, co-founder and CTO of Wisplorer. We are a VC-backed spin-off company from the research center VRWIS in Vienna, and we're experts for visual analytics software in power generation and distribution. My personal background is in human-centered analytics, where we have done many years of applied research in this field with industry companies like Austrian Power Grid, for example. And I also did my PhD thesis in the field. It was called Human-Oriented Statistical Modeling. So explainable AI has accompanied me for some years, actually. Okay, without further ado, let's dig into the topic. What is explainable AI? It is basically AI in which the results of an algorithm can be understood by humans. For example, with explainable AI, the human can understand why the AI takes a certain decision, how the underlying model looks like maybe, what assumptions the model makes, and under which conditions the model performs good or bad. As a very simple example, look at this decision tree on the right here. This decision tree helps to predict if a person belongs to a certain category. Like this. In such a model, the decision rules make clear why this model takes a certain decision. And you can even visualize how the model looks. And you can even visualize how certain the decision is here. So explainable AI is about transparency, interpretability, explainability. These are just some benefits of using such a model instead of a deep neural network, for example. Now, consider a more realistic example from the energy sector. Here we have a prediction of the natural gas consumption in a city as a time series in orange, and the measured gas consumption in black. If you only have the prediction like this, it's a black box. But with explainable AI, you can actually understand how the model works. Here, the prediction model is actually a four-dimensional regression model with 4 inputs. But how can we make this transparent? How can we visualize a four-dimensional model? Here's one way. You see here 4 input variables from left to right: temperature, wind speed, day of week, and time of day, expressed as hour. These are the inputs of the model. And on the y-axis, you see the gas consumption. This is the target variable that we're predicting. The visualization here tells you what the model predicts when you have certain values for the inputs. So here we are currently looking at the situation that the temperature is 0 degrees, wind speed of 3 meters per second on a Monday at 2 a.m. in the morning. And for this particular situation, the prediction of the model is around 86,000 gas units. The graphs show you what would happen if one parameter was different. For example, if just the temperature was warmer, the gas consumption would be lower. The steep slope of this graph also tells you that a slight change of temperature makes much more difference on the gas consumption than a change on the wind speed, for example, or on the day of week. So temperature is more relevant for explaining the gas consumption than wind. And such information is important for building trust in the models, because the domain experts can tell if this matches their expectations. And also, with such a tool, you can do a what-if analysis. For example, if I change the temperature here from 0 degrees to around 10 degrees, how does it depend on the other factors then? For example, you see that the daily profile is less pronounced in this case. Or what if the time was different? And so on. You see how the model changes. Also, you can validate the model together with actual data records. So each point here now corresponds to an actual measurement that we have to see if a parameter combination is actually realistic. Here, for example, strong wind speeds were observed much less frequently. You see just a few points. And this tells you that the confidence of the prediction is not so high in this case. And again, this is important information for building trust. So you see some benefits here: trust, confidence, and you also learn something about the underlying phenomenon. And these are some of the benefits of explainable AI. All right. So now if you look at a typical AI project, this interpreting of predictions is actually quite late in the life cycle, mainly after deploying a solution. But human input is actually not relevant only then, but throughout the entire life cycle of an AI project, which is shown here using the CRISP-DM process. In the beginning, for example, only humans can formulate the business problem and assess if the data available is suitable to achieve the project goals. Data understanding and preparation are very time-consuming parts of an AI project. And only humans can assess which parts of the data can be used. Maybe some parts are not relevant anymore, and an AI wouldn't know this. During the modeling, only humans know the application context of the models and can make the right trade-offs between maximal accuracy or a simpler model that can be interpreted. And during evaluation, humans need to assess if the solution is already good enough. For all of these things, humans need to be in the loop. Domain expertise is necessary and actually key for the success of the project. All right, and now let me illustrate this with some real-world examples and live demonstrations. All of the examples here are about human involvement in different steps of an explainable AI project. And the first example that I'm showing is about human-driven data preparation and modeling. And it is from Verbund, Austria's largest hydropower provider. It's about condition-based monitoring of a turbine. The turbine is an important asset, and monitoring its health is critical. For this turbine, we have a sensor for the oil temperature. And the plant experts want to define a dynamic tolerance corridor to generate early warnings whenever this oil temperature doesn't behave normally. So we have to model the normal expected oil temperature. Here in this image, we see 4 years of oil temperature measurements. And the challenge is direct modeling is not possible because large parts of the data don't refer to normal operation. For example, a maintenance period in here, shutdowns and ramp-ups of the turbine are also not a normal state we want to model. And also after the maintenance here, the normal operation was different, meaning the blue part is not relevant anymore. And all this knowledge is only known to the domain experts. Only they can carefully select the data that is relevant here and then continue with the modeling. And this I would like to show you now in a live demo. So let me switch here. Yeah. So what I have started now is our software Explorer. It's a tool for data analysis tailored to power generation and distribution use cases. You can load your data from many sources here. In this case, I will load a CSV file, but databases, Python, etc. are additional options. Now I load this data set from the turbine. And you see here, it's a time series data set in 4-minute resolution over 4 years. And then you have all these values that are recorded. Okay, you see that I have loaded a table with 500,000 records now, approximately. And one special thing about this blower is that you can start right away with one of our predefined analysis tools that you see on the left side here. Yeah, so without any configuration necessary, you can directly start one of these tools. In this case, we want to use a tool for multivariate regression. Now we have to tell the system what the target variable is. In this case, the oil temperature, and the rest are all independent variables. And with this, we can start right away. Let's begin by looking at the target time series, the oil temperature that you've just seen before. This is the oil temperature that you want to model during normal operation. Please ignore the plots on the left side for now. Let's not focus here. So we have 4 years of data here. Not all of it is normal operation, and therefore not all of it is useful for modeling. So this is the renovations period. I've shown this before. And during this renovations period, the system was also changed. So if you want to predict the future, only the time after the renovations is relevant. The experts know this, but it also becomes evident if you look at, for example, another input time series here, like this turbine flow temperature. You see this is how the system should behave. Like the variables should be very similar, and this was like it was before. So you see, after this renovations period, we can use the data for predicting the future. Back here, it's kind of obsolete. And yeah, we can do this just by selecting the time period here that you want to keep. Like in a drawing program, we can just select this data and then set the filter to only continue working with this. Right. So we see here some parts of normal operation, but we also see, and this becomes better visible when I zoom in, that there are also some shutdowns and some ramp ups of this turbine. And this is also not the normal operation that we want to model. We want to model this rather smooth state here. And to select this, in this case, I can do this also again graphically by selecting some of these regions. I'll just focus on a bit longer ones now. Here, where it was part of the normal operation. Okay. Just have to be exact now for the demonstration and just keep these. Right. And now we have mostly periods of normal operation with some gaps in between. This is okay. We can also in this visualization collapse the gaps so that gaps don't take so much space. See, yeah, maybe like this. Now we see a nice time series of data that we can use. We still have one more thing here that's a bit disturbing, and these are these small spikes here. And these are actually interesting because they occur during normal operation, where the oil temperature makes such a pattern. And this could actually be something that we want to detect with our dynamic tolerance thresholds. So what we can do here is we can just select them and label them directly in the software. So let's just label this as unknown ramp number. Okay. And then by scrolling through the data, we find the next and can easily, with one click, label this data here. There are a few more. Just repeat this for the two here. Here's one unknown ramp. Here is an unknown ramp. And I think the last one is here. So actually, data labeling is also something that you can do here along the way. And when we zoom out, we see here that we have our label and can highlight this in the visualization. These would be instances that our tolerance threshold that we model actually should detect later on. All right, now let's look at some input variables. And here on the left side, we see a list of the input variables. And this list is actually ordered in a way that those that are most useful for modeling this target variable are ranked to the top. So here, for example, we have the water temperature, okay, which is ranked to the top, and we can actually look at the direct correlation between the two and see here, for example, that we have on the x-axis the water temperature, on the y-axis the oil temperature, and we see by now this looks like a quite nice relationship already. However, what we also see is that we have two clusters in here that wouldn't expect at this point. And to find out what the clusters are made up from, we can select one of the clusters here with a lasso, for example. And then, for example, look again in the timeline. And then we see, aha, this corresponds mainly to this period here in the beginning after this maintenance. Also, with the water temperature, this looks a bit different in the correlation. So maybe this is also a part that we want to exclude because, yeah, maybe it has had to calibrate sometime after this maintenance, or for some other reasons it's a bit different. So let's go back here and filter this out and focus only on this part. And right here we can actually switch on a visualization of a regression line, maybe not only linear but quadratic. And then we can see that this relationship, oil temperature from water temperature, is actually something we can model quite nicely once we have selected the data. And even the dynamic tolerance corridor becomes quite evident here, because you see that roughly around 1 degree degree Celsius around this regression line is normal. And then you have these unknown ramps here that you see, which would actually be detected by such a rule. If you say more than 1 degree apart from this prediction should be detected. Okay, and we can actually do the modeling here in the tool. For this, I also filter out these unknown ramps now because I don't want to use them as a training data. So let's exclude them as well. So we have really clean training data. Okay, again, maybe a word on the list of input features here. This list here is ordered in order to help us select the useful features. We've heard today that feature selection is a challenging problem or a challenging topic in itself. And this list basically is ordering the features to help us choose those for the regression that have the best or the clearest relationship with the target variable, even nonlinear relationships. Water temperature is top ranking, and so this algorithm guides the domain experts towards the features that they can use here. If you're interested, the metric behind this just looks for each feature if the local variation of the target variable is smaller than the overall variation, because then this input feature tells us something about the target. This makes it also detect nonlinear relationships, like for example here, if you take the month, but actually the temperature is more useful here. And now we can actually model this here in the tool. So we can say we want to create a new regression model using the input water temperature. And by doing this, we have got a polynomial regression model here. You see the graph of the model here. You also see the model definition down here. So basically we have a polynomial up to 4th order using the water temperature with these coefficients. This is quite nice, but you see that there is also still some variance left in here that is not explained by the water temperature. And for this purpose, this list on the left here has updated now to help us find features that can explain the remaining variance. And now you see top ranking, for example, is a feature here called turbine part 2 position. I'm not completely sure, but I think it's a mechanical feature of this turbine that also, as you see here, explains some pattern that is in the errors of this model, which tells us we might gain something by including this in the model definition. So let's add this feature, make a new model variant that is two-dimensional based on the water temperature and this turbine part 2 position. And now you see, as in the slides, you basically have a visualization here of this two-dimensional model, where again, we could do a what-if analysis and see, okay, if the water temperature is higher, how does it then depend on this second feature, for example? So we have our two models here. The first one had only one feature, the second one has two features, and we can see here that the RMSE has gone down, for example. And it's actually quite quick to end up here with a explainable model of this oil temperature here. Maybe also just one thing, we have these unknown ramps here that we had excluded. So maybe let's include them again in the visualization and look at the actual prediction that we have made here as a time series. And you see here now, our prediction time series is in blue and the measured values are in black. And you would nicely see that these unknown ramps that we have in here are quite strong deviations from our expected modeled behavior. And by defining a threshold here, for example, like 1 degree or a bit more, these would actually be able to be recognized for condition-based monitoring, for example. And when you have trained such a model, it's also possible to export it here as a Python code, for example. So you see here the formula with the coefficients and everything, which you could copy to the clipboard if you want to continue working with this, for example, in a Python environment. Okay, this concludes the live demo of this use case. Let me jump back to the presentation. To summarize, what are the results here? After selecting the useful data based on the domain knowledge, we now have an explainable model as a basis for dynamic tolerance bands. If we compare this to a static tolerance threshold that wouldn't depend on other variables, this allows the experts to detect the deviations much earlier. And what this example also nicely shows, the explainable model is just a part of the whole story. Without the domain expert carefully selecting the relevant data upfront, the modeling would not have been possible. So it shows that the human input is necessary in multiple steps here. Moving on to a second real-world example. This one involves the humans in the evaluation phase. And it is about forecast validation and diagnostics. One challenge for asset managers is the exploding number of prediction models they have to maintain. With decentralization, renewables, metering of customers, and just the possibilities that AI bring to the table, the number of models is growing and growing. Here, in this example, we have prediction models for power load from different regions. And the challenge is to validate all of these models regularly. Because sometimes the models need to be recalibrated when the consumer landscape has changed, for example, or other structural breaks have occurred in the market or in the system. But from hundreds or thousands of models, how can you quickly find out where action is needed and what action is needed to improve the models? Again, let me show you this in a live demo. Now, this is related to monitoring actually. So of course, this should be linked to live data. And it's possible in this Explorer to access a live database and to give the end user an entry point that is as simple as double-clicking a file. And when I do this, I am just asked which larger geographic area I want to load from the database. And yeah, the models in this case are power load forecasts from consumers in this area. So area 1 is fine. And also the time range that I want to analyze can be selected. But I just press OK now, which loads the relevant data from the database. Okay, and now I'm in my monitoring cockpit. The first thing that I see is an overview which forecasts have become worse in the last 3 months. So here, each row refers to one model, and you see the error for these 3 months compared to the error in the most recent 3 months. And you see here that for the first model, the RMSE has gone up by 29%. For other forecasts, this was not the case, or not so much. Yeah. But here we have this issue. So around October, a drift here started to happen between the predictions in orange and the measurements in black. So let's focus on this problematic period here and look at it in more detail. Let's filter. And let's zoom in a bit here on some example period. Can turn off this trend overlay now. So, and you see here this drift, right? Also, there are other views now to look at these errors to find out maybe what was going on. For example, a heat map view. Again, you see the forecast models here as rows, and the cells here show you the error, in this case RMSE, per day. So this means a red cell is a day with a large error. And this allows you to spot problem days easily. For example, you see here that for the same days, multiple regions here were affected, but not all of them. Yeah? So sometimes the errors coincide across regions. Let's zoom in on an example here. Focus on a few models here with the problems, and then select some of these days. Now let's try to diagnose these errors. For example, we can look at other variables and see what they were doing at these times. So here we can open a view on independent variables. A little bit bigger. So, and you see here a list of independent variables, quite a long list. And the top ranking ones are those where the large errors that we see in red here concentrate with respect to the values of this variable. And for example, we would see that for temperature B, large temperatures over 20 degrees coincide with the larger errors. So for warmer temperatures, right? So again, this ranked list is an algorithm that guides the user towards relevant features from a potentially quite long list. Let's look at a longer period if this still holds. And indeed, it seems as though the temperatures were still high during many of these large errors that we see down here, but not for all of them, though. So this warm temperature is probably not the root cause, but such information gives clues about situations that are not modeled well enough, right? And if you know this information about systematic errors, it helps you to actually improve your models, because including such effects better in your model definition can help to reduce the systematic error and make the models better. All right, so let me switch back to the presentation. What were the results here? The asset managers have a scalable overview of which models need to be improved, and also some hints on how to improve them. And one takeaway here is also this: even though the models may be black box, which is the case here, they are externally computed, it's still possible to make transparent why errors occur or when errors occur. And this is key information for improving the models. All right. And the final example refers to data understanding and data preparation. And it is from Energie Baden-Württemberg. It is about optimizing the ramp-up procedures of a coal power plant. Ramp-up means that the power production is increased or ramped up to a higher level by the operators of the plant. Why is this done? With an increasing share of renewables and with more dynamic grids in general, it's often necessary to redispatch power production. For example, by ramping up a coal plant. Here, you see 3 ramp-up events. You see, by burning some coal and some gas, the production is ramped up to a higher level. Ideally, this is done by using not more fuel than necessary, especially gas. And the problem is this: such power plants are highly complex, with a lot of interdependencies, and certain constraints are also imposed by the authorities. So optimizing this needs a lot of care and manual work by the domain experts, like labeling the ramp-ups, inspecting them, defining and comparing some KPIs. So the human here is not just in the loop, but actually in the driver's seat. But good news, even for such cases, we can use explainable algorithms to assist the human task. And I will show you this in a live demo. Right. I'm back in Explore, this time in the cockpit pattern search and comparison. Let's start by looking at this net power time series. This is the amount of energy produced. And you see it here. Let's zoom in a bit. So here you see startup of the power plant, right, from 0. And then afterwards you see some of these ramp ups or redispatch events. This is when the operators are notified about more power or less power being necessary. And this ramp up is achieved by burning coal or by adding extra gas. Okay, you see here how the gas is added. And it's a goal to keep the amount of fuels, especially the gas, low. To optimize this, the asset managers want to analyze this data not in the raw time series, but actually in terms of the ramp-ups. So how much gas is used per ramp-up? And for this, we need to segment the time series into these ramp-up procedures. And this is supported by the tool with a pattern search feature. So let's focus here on the net power again, on such a ramp up, and then select one example of such a ramp up. 1 hour 50, yeah, not. And then search for it. Let's call it ramp up. All right. And this searches in this time series whenever a similar pattern occurs. By default, 9 patterns have been found. You see them here overlaid on top of each other. You also see them down here in the time series when they were. And here you also see the exact times when they happened and also some statistics for each of them. Now the question is, what is a similar pattern? And this interface here supports the user in choosing the right threshold. So we can adjust this threshold, for example, maybe make it stricter. We only find 2, which is the most similar pattern here. Or if we include very many, you see, yes, we're finding many, but also some very different ones. So this visualization actually helps you to choose what threshold makes sense. And then 47, this looks not so bad. Because if I increase it, also some here come that I don't want maybe. This looks actually quite good with the exception of this one outlier here. So maybe I'm happy with this threshold and say these are the 47 similar enough ramp ups that I want to analyze. Let's get rid of this one outlier here by selecting the bundle of ramp ups that I want to keep and say keep only them. And now you see all the 46 by now ramp ups next to each other down here. We can also add the amount of natural gas here. Zoom in a bit. You see nicely how the gas is consumed, especially in the beginning of each ramp up. You also see this up here in the overlaid form. And you also see when each ramp up occurred together with some statistics like the amount, the sum of gas used for the ramp up and the sum of power produced. In here, you see also that there are some extreme cases where more gas is consumed. So let's just select them here and inspect the cases in detail, for example. Yeah, and we want to reduce the gas consumption here. So what we also can do is we can sort all of our segments by the amount of gas used to find quickly those where the most gas was used. And by looking at this list, we see, okay, there are 46 of them. There are many of them actually that have more than 90,000 norm cubic meters here. So we could say this is actually a lot. Let's select these 14 gas intensive ramp ups, and we can give them a name as well, and name them, for example, high gas. Okay. So again, we have labeled the data and have identified our high gas consumptions. And with this, we can also filter on them because now we want to focus really on these cases. So we're looking at 14 cases where the most gas was consumed. Now the users actually already like this visualization down here as a basis for discussion, because also the shape of this red gas curve tells a story to them. Yeah. We also see here in this curve view up here, we focus on the natural gas maybe, no, sorry, on the net power, that not all of these ramp ups are actually the same. Yeah, there are still some clusters in here. And you see, for example, that there are some, like this one, that doesn't go up so high in the power. Yeah, it starts actually quite high if you look down there, and actually doesn't come up all the way to the top. So the delta or the power increase here is lower than for some of the other ramp ups here. That's basically okay because it's requested like this by the authority how much they should ramp up. But if the ramp isn't that big, the use of fuel should also be lower, and we can investigate this. Actually, we can order the ramp ups here by the height of the ramp up. So let's not choose the sum here, but we can choose another statistic, maximum up here minus minimum. So really the range that they make. And order this by this metric. And then we see, for example, here I have the 4 ramp ups that made the smallest increase in power. And I can label this again and call that low ramp. And make this labeling called ramp height because we're just about to label the other ones as well. So these are the low ramps. And then up here, you see, for example, all over 58 are the high ramps because they go up to the top. Let's label this as well and call it high ramp. Okay. If we now focus on these 2 categories that we have just labeled, we can also visualize, for example, the average curve and some boundaries around each of them. To visualize the 2 clusters that we actually have here. Remember, all of these ramp ups have used a lot of gas, more than 90,000 norm cubic meters. But there are distinct differences here, how big the achieved power ramp up was. So the blue ones are actually those we would like to optimize. Yeah? At this point, we should also include coal in the analysis because gas is not the only feature. But looking into this, we find also out that the coal consumption was not explaining this difference. And let's take a look at the situations in more detail here. Yeah. And let's focus just on those with the low ramp. All right. So these are the 4 most gas inefficient ones. And from this, the experts found actually quite interesting things. So first, three of the four actually were quite early in the day. Yeah, so at 5, 6 a.m., earlier than usually these things happen. Also, three of them, when you look at the coal here in gray, three of them actually have a dent downwards, so this dipping downwards of the coal before the ramp up really started. And also you see some fluctuations of the coal in here while going up. These were some things where the plant experts actually said this is something that they want to investigate and discuss with authorities and operators to find out what was going on during these ramp-ups. And this was discovered by looking at these plots after segmenting. And for the first time, actually, the experts were able to perform an analysis of ramp-ups like this, segmenting the data and localizing problem cases for further investigation. This is actually a quite new project, and we're actually looking forward and interested in how this analysis continues. All right, let's go back to the presentation and summarize the results of this. For the first time, they could analyze in terms of ramp-ups, and they have generated ideas for optimization within a few hours. Also, this segmentation approach gives them massive time savings for their quarterly reports of ramp-up efficiency, because this was a mostly manual and process of inspecting the things and reporting it. But now with this segmentation logic, these reports can be generated much faster. Yeah, this third use case was actually a nice example of how analytic guidance, visualization, and interaction work together to guide the domain experts in tackling such complex problems. Hey, finally, a few words about Explorer, the software that you saw. It's a plug-and-play software for self-service analytics with a focus on data exploration and data preparation of time series in much less time. What do I mean by plug and play? As you've seen, there are ready-to-use tools for all the questions I showed in the demos: regression modeling, model validation, pattern search. No customization was necessary for this, but they were standard features that you can apply to your data in 1 minute. Why is this possible? Well, because we have developed it over more than 10 years with customers from the energy sector. So it's actually tailored to recurring questions of power generation, distribution, and other energy topics. Also, as you have seen, it integrates directly with databases, Python, and many other sources. And Explorer is in use by leading companies worldwide. Here you see a few examples by the logos. If you would like to try it out or see a live demo, please just contact us. There's an email address on the last slide or in the B2Match tool. All right, let's draw some conclusions here. First, we have seen that explainable AI is not just an island, but actually a process. The domain experts do not just interpret the results in the end, but they play a key role from the very beginning of the project until the end. And the benefit of having humans in the loop can be a solution that is more trusted and more backed by the domain experts who actually use the solution. And finally, some problems may not be ready for AI today because they require so much experience and domain background. But in this case, even if you have such human-driven workflows, we have seen that bringing algorithms into the loop can make these workflows much more efficient, to guide the users and also to free them of the most time-consuming parts. With this, I would like to thank you very much for attending this workshop, and I'm happy to take any questions. Please post them in the chat if you haven't done so.